So at this point, we already have a working knowledge of the basics of momentum, what gives an object momentum, of course. Momentum is p, it's mass times velocity. And we also know the basics of impulse, change in momentum, which is not only your final momentum minus your initial, but it's also the force, the net force that was on the object times the time that it was applied. What we're concerned about now is we're going to start looking at situations when where objects interact, where there's collisions, where a single object, say for example, explodes into multiple pieces, or in the case as you see before you here, when two objects, me and Shaquille O'Neal, you guys are getting, I'm getting old enough that people probably don't even know who Shaq is now. It's like, who? But anyway, he's obviously larger than me, and that's all that you really need to know. So we go roller skating, and by the way, the whole point of roller skating is to remove friction, right? We're saying there's no friction. Avoid that complication. And so we're going to look at a situation where a single object, really, we're going to consider, as we'll look at in a moment when we talk about these two things here, where we can look at this as a single object where it splits apart into two smaller objects, and how we can use momentum to make that situation easier. So, which leads us to the following. How we view the situation. See, we can look at this and define the system. In this case, I can think of three different ways to define the system. I could look at just Shaq. I could look at just myself. Or I could look at the two of us as one thing, one entity. Not that we have to be connected all the time, but in fact you can include multiple objects that can be really nowhere near each other. You could look at the solar system, for example, as a system. Well, it's called a system, right? Solar system. So, but as a single entity and how it reacts to some external force, like the gravity from the center of our galaxy or something like that. So how we view this is going to make all the difference in the world. And what I mean is this, is when we can look at the forces on a system, and we can determine that they are all internal to the system. In other words, things that are in our included system acting on each other and not being acted on by some outside force that's not in the system. When we can do that, when we can verify that all the forces are internal, then we can say that momentum is conserved. Now, what that means is that when momentum is conserved, we know that the initial momentum of the system has to equal the final momentum of the system. It's a very simple, quote, equation, but it is very powerful. It helps us out of a lot of more difficult situations. But this only is true if we can define our system in such a way that all the forces that are acting at any given moment are internal to the system. If we can't, then I can't say that momentum is conserved. That means the forces would be external. For example, in our situation here, that's why we talked about eliminating friction. Because friction would be, no matter which one of these three systems I've chosen, friction would be an external force, and the momentum wouldn't be conserved. Which makes sense. We'd slow down, for example, right? And our momentum at the beginning wouldn't be equal to our momentum at the end. But if we could ignore friction, for example, in this case, and the best way to look at this, to keep things as simple as possible, is to keep all the forces internal by looking at the system as the two of us, then we can assume this, and this problem becomes, well, the problem I'm going to pose to you in a moment, this situation becomes easy to deal with, or easier at least. So, what does it mean in this situation to say that momentum's conserved? Well, that means that our momentum before an event, that it only involves the two of us interacting, has to equal the momentum after. For example, let's say that we are just stationary in the middle of the rink here, ice skating. By the way, we're ice skating. That's why we're frictionless. I didn't try to draw our bodies, but there's wheels. We're good. All right? So we're just standing there, completely stationary. Our momentum then, at the initial part of this, would be 0 kilogram meters per second. Wait a second. That means if all the forces I'm about to describe are just between the two of us, they are internal, and that means our final momentum has to be 0. So, interesting. So we're going to go in this scenario. I say something that Shaq does not agree with, and he pushes me. Now, this is where Newton's third law comes in. You can't get a single force. So we know that if he pushes on me, if Shaq pushes on Wellborn, then Newton's third law says, even without trying, Wellborn will push just as hard back on Shaq. So we both, by the way, this is why internal forces, if we consider them internal, this is why we don't change momentum, because Newton's third law. But both of us would experience the same force. Think about that, right? Newton's third law says it has to be the case. The force that Shaq puts on me would, of course, be that way. Force by Shaq on Wellborn. The force, the Newton's third law force that goes with that, which would be the same, so I should really make sure that I draw it at least looking somewhat the same. This force by Wellborn on Shaq is going to be exactly the same. Wait, so we're no friction, so we're going to both accelerate in our respective directions, and we're going to pick up speed. Shaq's going to pick up speed in this direction. He's going to accelerate that way. I'm going to accelerate this way. So you might be saying to yourself, well, Wellborn, if both of you are moving, you both have momentum, there's no way that can be 0 then. But you would be forgetting one important point. Momentum, unlike, say, kinetic energy, is a vector. And Shaq's momentum would be, we'll say, negative. Going to the left, we'll call it negative. That would mean my momentum would have to be positive. So, guess what? If you have a negative quantity and a positive quantity and you add them, guess what you can get? So this brings up the point that there's actually more than one way to get 0. You can have nothing, or you can have a lot and then lose a lot. Either way, you're at 0. So it would be true that the final momentum would also be 0 kilogram meters per second. Which, okay, that's kind of boring, right? But this can be used to find an awful lot of information about the situation. So, for example, I can start with that idea that the initial has to equal the final. And I could even say, in this case, by the way, different situations, this may not work out exactly the same, but let's do it this way, actually. Let's break it up before I get to the specifics of this case. Before anything happens, it would be, we're one object, right? So mass of Shaq plus mass of Wellborn, that's our total mass, times our velocity at the beginning. Now, we all know this is 0 because we were stationary. But it doesn't have to be. We could be skating along at some constant velocity, have a momentum, and Shaq could push me then. Still wouldn't make a difference. We could still solve this, use this to solve the problem. 0 just makes it a little simpler. Afterwards, we are not one harmonious object. We are two separate objects. Shaq has his mass and his velocity, which would now, we'll input afterwards here. So Shaq's velocity after the incident between us. I'll use plus. Right now, one of them is going to come out negative. We know this. But combined with mass of Wellborn, my velocity afterwards. So notice this really simple statement, depending on the situation, can be broken up in any number of ways. Here we have a situation where we have one object that splits into two. You could have two objects that collide with each other and stick together and make one. Or you could have two objects that collide and bounce off each other. So you start with 2 and end with 2. There's all kinds of possibilities for types of collisions or so forth, interactions. This is just one, where I start with one object and I break up into 2. This could also, you could also look at this as somebody firing a gun. The gun moves backwards, that's the kickback that you might be aware of, and the bullet goes forward. Each of them, all right, would have, in this case, if they started at rest, they'd have identical momenta. So, like we said, we started with nothing because we were just standing there in the middle of the rink. So if we knew, let's say Shaq's mass, Shaq's velocity, final plus Wellborn's mass, all you need to know now is 3 of these 4 things, and you can find the 4th. Basically is what we're looking at. So for example, if I told you that Shaq had a mass of, let's say, 100, whoa, that was unexpected, I'm not writing there, 140 kilograms. And let's say, well, we'll discuss the velocities. And my mass, we'll say, is half that, 70 kilograms. All right, now, whose velocity would you expect to be more? Well, wait, they experience the same force, right? They should have the same velocity, right? No. Don't think that. Stop. Don't make that the only thing you remember from this. All right? No, they're not going to have the same velocity because they have different masses. So you apply the same force on 2 objects. If an object's small, they're going to accelerate more rapidly, and they're going to pick up more speed. So we would expect me to go flying and Shaq to move backwards at a slower speed. And in fact, you'll notice, whoops, come on. There we go. My board's acting up on me. But you'll notice that Shaq's mass is twice as big as mine. That's a nice convenient number here. That means if I'm going at 4 meters per second, how fast is Shaq going to go? Don't tell me 8, please, right? Because that would give him more. He would be going half of that because he's got twice the mass. He's going to be going 2, except, pardon this writing here, there we go. 2 meters per second, except which way is he going? Yeah, his would be negative. Because what do I need this and this to add up to? I need to add them up to 0. So, let me see if I can save myself here by bringing this down. So I know that 0 equals, in this case, 140 times negative 2, and these are all made up numbers just to illustrate the point. So this would work out to be 0. So all you really needed to know would be, of these 4 things, 3 of them, you could find the last one. Okay, so we're going to use this idea to solve problems. This is a really simple idea to write, but because it could be applied to many situations, sometimes getting from this statement to what this is going to look like, and this, what I'm circling right now, that'll be different from situation to situation. I can't tell you, I can tell you right now, is if you have one object that is at rest, well, one object that's moving at constant velocity, and splits into 2, yeah, this would work, except you wouldn't use Shaq and Wellborn, it'd be, bullet and gun or whatever. But that's just one possibility. There's all kinds, and we're going to try to look at all of them one way or another. And we're not even talking about working in 2 dimensions. We're all just dealing right now with 1 dimension. All right, so pay attention as we go through, and I think it's being helpful for you to think about, if I looked at just myself, Shaq's force would be external, and I would experience a change in momentum, wouldn't I? And in fact, if you knew the force that Shaq applied on me, and the time with which he applied it, you could find my change in momentum, because I went from 0 to having some momentum. Remember, we're just looking at me as the system, not both of us. How would Shaq's impulse compare? Well, could his force be different? Newton's third law says it can't be the same force. What about the time that he applies it? Could the time he pushes on me be different than the time that I push back? As long as we're in contact, that time has to be the same for both of us. So he experiences an identical impulse, but the other direction. So therefore, if we both experience the same change in momentum, when you look at our two momenta and you add them up, it's going to be 0, because one's negative and one's positive. So there's another way to look at it.